welcome to the next session. Very pleased to announce Charlotte Werndl, who is a philosopher until recently at the London School of Economics, but recently taken up an appointment at the University of Salzburg, and she's going to talk about defining climate and climate change.
Yeah, thank you, Wayne. And then first of all, let me thank the organizers for organizing this very interesting conference. Thanks, and also for inviting me. It was a pleasure to be here. Yeah, thanks for that. A bit about my background. I mean, Wayne said I'm a trained philosopher, and I'm a philosopher, but I'm also a trained mathematician, and especially with a background in dynamical system theory. And this will also explain some of what you see. I will use very simple systems from dynamical system theory to illustrate the claim, because I think it's easier for you to understand it anyway. Good, but what's the question? The question is really how to define climate and climate change. And so just to motivate the question, why is the question important? And first of all, how to define climate and climate change is by no means trivial and actually quite contentious. And I have here one quote, but I mean this quote could be easily also from today. It's also nowadays quite contentious how to define climate change. So here Todorov, a climate scientist, writes, the question of climatic change is perhaps the most complex and controversial in the entire science of meteorology. No strict criteria exists on how many dry years should occur to justify the use of the word climatic change. There is no anonymous opinion and agreement among climatologists on the definition of the term climate, let alone climatic change, climatic trend, or fluctuation. Just an expression that is quite contentious how to define climate and climate change. And I mean, why is that important? You might ask, well, it's just about the term, why is it important how to define climate and climate change? And first of all, it's important to avoid conceptual confusion. That's clear. So if different climatists or the general public has different ideas of climate in mind, this can lead to a lot of confusion. And second, of course, which will become clearer what I mean by this later on. So if we have a definition of climate, for instance, which doesn't really tell us much about the actual climate system, but just about some hypothetical climate system, that's not very useful. So we need a definition of climate with which we are able to make true statements about our actual climate systems, and not just about some hypothetical climate systems. Good. And as I just said, I think conceptually there are a lot of different definitions in the climate literature, and there's certainly scope here for philosophical analysis. So just a quick outline of what I will be doing. So this was the introduction. I will then start with introducing the basic terminology, climate variables, and the simple climate model, which will be our simple climate model we work with, just because it's simple, but you could in principle replace it, of course, by much more complex climate models. Then I'll talk briefly about what we want from a definition of climate, so certain basic requirements on a definition of climate. And then I discuss what I take to be the two main kinds of definitions of climate, which you find in the literature. Climate as distribution over time. There are three versions of that, and they're actually quite different, the three versions. And then climate as ensemble distribution, as I call it. And again, two versions here, and then I'll conclude the discussion. So let us start with climate variables, the basic terminology, and the simple climate models, which I will use to illustrate the claims later on. So when you talk about the climate, you of course talk about some things. There is like temperature and so on, surface pressure, and these are called the climate variables. And they, of course, usually include the variables that describe the state of the atmosphere, so the weather. So sometimes you hear this idea that climate is the expected weather, or climate is the average weather, which seems to suggest that only the weather variables are of interest, but this is usually not the case. So usually you're also interested in the ocean, and sometimes also other variables. It really just depends on which paper you look at. Sometimes also those variables describing glaciers and ice sheets are also included. But what's important now, there can be a bit of variation here that doesn't matter so much for what follows, but these variables which we talk about when we talk about the climate, they are called the climate variables. And now to what I say here, assume true simple climate model. So we will, for what follows, because it will be particularly easy to understand if you do it that way, I will assume that the following simple climate model is just the true model of the real climate system, which of course it is. It's evident, but we'll assume that is our true climate model. And what do we have in the climate model? We have a temperature, just one climate variable for simplicity, the temperature, denoted by xt, the temperature at day t. So we work with discrete steps here. Again, you could work with continuous time steps too. We just do it for simplicity, we work with discrete steps. And we say that the temperature range is between 0 and 30 degrees Celsius in this case. And this is our temperature evolution. So what we have here, we say the temperature at day t plus 1, xt plus 1 equals, and you see that equation here, as it is function f of xt, and what is this? So quite simple. If it's between 0 and 15, it's 80 xt, and if it's between 15 and 30, it's 80 30, means minus xt. And what's important here, so what do you have here? You have that at, that's the external conditions, and they can depend on the time. That's why you have that's why you have the subscript t here, at. And in that case, just for simplicity, we'll assume that it's the solar energy reaching the Earth at day t, and it's periodically fluctuating between 1 and 2. So on one day it's 1, and the next day it's 2, then it's 1, and it's 2 again. It's just to have some kind of model where these external conditions aren't constant, because of course for the actual climate system they aren't constant. And so let me just quickly show you how this looks like. So if at is 1, for instance, then you have this picture. You start, this is your temperature, 0 to 30, and if at is 1, what the function or the map is doing, it maps it to some value between 0 and 15. So this is when at is 1, and if at is 2, what you have is a map like that. To those who are familiar more with dynamical system theory, this is really the tent map blown up to the tent map which usually considered on the unit interval 0, 1. Here it's blown up to 0, 30. But this is essentially what you're doing here. You have a very, very simple dynamics here, of course. You see from these illustrations. It would be hard to find anything much simpler. And we will work with this, and I will give you then, so when I later talk about the climate distributions, they all come from this model. Okay. So, and then finally, just some requirements on a definition of climate. So the question is, what do we want from a definition of climate? And the first point, I think, is quite uncontentious. We want, and the definition of climate should be empirically applicable. So we want to be able to do something with it. And in particular, of course, we want that it relates to the past and future time series of observations. So if we have good observational records, we want to be able to estimate the climate from it. That's the idea underlying here. And then the second one is the idea that if there's, so to speak, clear agreement that two climates are different, we also want that our definition comes to the same conclusion, that the two definitions, that the two distributions correspond to different climates. The third one, I actually won't need it in the generality, right? It's not dependent on the knowledge. All I will be needing is that it's not dependent on our knowledge of the uncertainty we have of the present, of the climate variables. But the idea is here, climate is something objective out there in the world. Our knowledge of the climate is of course dependent on us, what we know, but not what the climate itself is. And then 4, I think we want the definition of climate that not only is about the future climate, but about also the present climate and the past climate, not least because only if we have a notion of past climate and present climate, we can define climate change. And 5th, this is a bit in the background here. So this definition, this presentation is mainly intuitive. I won't give much mathematical detail, but all the definitions I'm presenting can be defined rigorously in autonomous and non-autonomous dynamical system theory, and I have a paper about that if someone is more interested in the mathematical aspects. So, but the 5th aspect just said we want a definition that makes mathematical sense. It doesn't refer to limits that don't exist and things like that. Okay, so this was really to prepare the debate. So let's have a look at the different definitions now. We'll start with climate as distribution over time. As I said, there are 3 versions and they're actually quite different. I start with the first version, which you find many climate scientists discussing and endorsing, Lawrence for instance. And what is the underlying idea here? I mean, here you start with the idea that the external conditions, so like the AT we had in our model, takes the form of small fluctuations around a mean value C over a certain time period. So why do you do that? The idea is, well, at the present the external condition take, of course, a certain value, and we just assume over the time period we have a look at that it's roughly just fluctuating around a certain constant value. And because it's conceptually easier, and as well as we will see, I mean, one reason why people do that also, assuming that these constant external conditions, is because it's mathematically just so much easier to work with constant external conditions, because then you're in the framework of standard analysis. Okay, and so what is then the definition one? It's just that you choose your mean constant external conditions, and then you say the climate over this time period, over a certain time period you're considering, is the finite distribution over time for the true climate model under constant external conditions. So I'll make that, I mean this is the general definition, but I'll make it clearer now with our example. So what exactly are you doing here? So let's go back to the example. I said it fluctuates, on day 1 it's 1, then it's 2, then it's 1, then it's 2. So of course the mean here is 1.5. You, for instance, choose the time period you're interested in, the 1st of July 1983 to the 30th of June 2013, and I want to know what the climate in that period is, the climate of that period. And of course we know from our simple climate model, it's just always fluctuates around C equals 1.5. So we take C equals 1.5. And then we say the climate over this period is then simply the distribution over time which arises when our model, with these constant external conditions now, we just set it constant, and with an initial value, and just assume that this is the initial value of the climate system on the 1st of July 1983, is evolved forward over 30 years. So basically what you're doing, you start with your initial value, and every day over 30 years you look at all the values you get from your climate model, and then you calculate what I said here. A subset of A is assigned to value the number of days with a temperature in A. So you look at your time series, you get 40, 30 years. Look at the number of days with a temperature in A and the total number of days. I've ignored here gap years because it doesn't really matter. You can just include it here. But this is what you get, and when you do that, you get a distribution or a measure, which we see here. And this is for our simple climate model. That's then the climate over this period, 1st of July 1983 to 30th of June 2013. And you see in that case, it's just very centered about here in the middle, in the range in the middle, 15 to 20 degrees. As I said, this is one popular definition. I think the main problem with that definition is this assumption of constant external conditions. So why is this a problem? Let me explain that in a bit more detail. So as I said, you have to assume, of course, for the real climate system, or for our more realistic climate models, the external conditions aren't constant, because things are constantly fluctuating. And so if you're a proponent of that definition, you have to assume that this constant external condition doesn't really matter, in the sense, that when the external conditions are just small fluctuations around your constant mean, then the distributions you get are essentially the same than those you would get if you just work with the actual external conditions. There's such assumptions you have to make to be a proponent of such a definition. And I think, the best thing, of course, would be to test it with the very realistic climate model, but we don't have any such thing, I think. So, but there are doubts about this assumption when you study some models. And so, I'll illustrate these doubts with the simple climate model, but they can be carried over and can be substantiated with more complex climate models. So in reality, what's going on? In reality, you of course know that these external conditions, they fluctuated between 1 and 2. So not constant, but there was this constant periodic fluctuation. So the actual distribution over time, in principle what you're really interested in, is given by the actual evolution of the temperature with the same initial value, the same time period, 1st of July 1982 to the 30th of June 2013. So what you're doing, so the actual climate distribution you get, if you do the same thing as before, so you start with your initial conditions, you evolve the system forward on a day-by-day basis over 30 years, but now just with the actual external conditions, not with the constant ones. Otherwise, you do exactly the same. You again look, if you ask what is the measure is assigned to a subset of A. You take the number of days of your time series of those values that were in A divided by the total number of days. So same thing, but just with non-constant external conditions. And what do you get? For that model, interesting, you get that distribution. So you see, I mean, it's evident that if you, I mean, this is just a very simple model, of course, but it's evident that this distribution is actually completely different from that distribution. And so this is the actual temporal distribution over time for the simple climate model. The other one was under constant external conditions, and they are quite different. And as I said, I mean, this is just really, of course, I worked with the simplest model in a way I could think of, but you can use, I mean, there have been studies with more complex models too, but you also find that it actually makes a crucial difference. You can't just assume, even if it's not fluctuating that wildly, you can't just assume that it's constant. It will give rise to different distributions. So there's the problem here that if you use a definition like definition 1 with constant external condition, you might use a definition which just tells you something about the model, but not really anything about the real world. This is what I mean by empirically void. It might not be empirically applicable. It might not fulfill your what I call desiderata 1, this requirement 1, that it's clear that the definition is applicable. But that's the problem with this definition. And so because of this problem, we think, of course, now let's take the external conditions into account and let's acknowledge that they're varying. Let's see how we can do that to arrive at a better definition. And this is now where definition 2 comes in. In a way, definition 2 does the most, in a sense, obvious thing in response to that, and says, well, let's just define climate as the actual statistical distribution we have over a certain time period. So, this is what's stated here. So the climate over a certain time period is just define an actual distribution over time for the climate system, for the actual evolution of the climate system. And of course, that makes the climate immediately very easy to estimate from the observations, of course. That's very neat, and that's why some like the definition a lot. It's easy to estimate from the observations. And I mean, to come back, this is what we've seen before, and this is what we have calculated before. This is your actual climate, this is your actual distribution over time. If you start with definition value, the 1st of July 1983, the 30th of June 2013, you get that actual distribution. And some like to call that the climate. Good, then, as I said, I mean, this is quite nice because it's very neatly related to the observations and to your records of observations and to past time series of observations. I think that, though, that you have a problem, which I will try to explain with that example. So, you think about the climate usually as something, a distribution, given a certain configuration of the climate system, and that definition doesn't quite do that, which I can illustrate now with this hypothetical scenario. Suppose, as I write here, so you have a time period, T0 to T1, and just in the middle, between T0 and T1, the Earth is hit by a meteor, and of course suddenly the whole system completely changes, and as a result of that there's lots of dust in the air, the climate is becoming colder. And in that scenario, I think we would agree that the climate before and after the hit of the meteorite are actually different. But the problem is that definition 2 doesn't necessarily imply that in the following sense. So all the definition 2 says is just climate is a distribution for the actual evolution of the climate system. It doesn't tell you that you're only allowed to use certain time periods and others not. So in other words, it doesn't preclude you from just saying, I just want to look at the statistical distribution from T0 to T1 and call that my climate. So I think the problem we have with the definition, unless we say anything more about which time periods we're allowed to take or not, and this definition doesn't do that. This definition only says climate is a distribution over time, over some time period. And we run into problems. And so I would say definition 2 has a problem with this meeting the desiderata 2, that we have situations where I think we have different climates, but the definition doesn't necessarily come to that conclusion. Okay, then definition 3 here, in the sense, what it does is it corrects for that. It's again a distribution over time, and what does it do? It says, well, climate is something like a distribution distribution given a certain regime of varying external conditions. So that's the first line here. You say that the actual external conditions are over a time period subject to a certain regime of varying external conditions. And then the climate is simply defined as, again, the finite distribution over time which arises under that regime of varying external conditions. So let me spell that out a bit more. With the simple climate model, what you do is you say, well, this regime, so when it fluctuates periodically between 1 and 2 and 1 and 2 and so on, is just a regime of varying external conditions. This is one of the regimes. And you say that AT, in that case it's of course particularly simple, was subject to this regime from the 1st of July 1983 to the 30th of June 2013. And so what you do is, really like before, you say this is not my regime, I start with my initial conditions. As before, I take the same time period here, and what I get is calculate again the distribution, calculate so how often the system was in a set A divided by the total number of simulations I did, and what I get is again 2 or 3 in that case. Because it's such a particular simple case, in that case it just coincides with the actual climate distribution, because your regime of varying condition is just, in that case, what the actual climate system does. So, so this is distribution over time. I think this definition, if you look at distributions over time, I think the third definition is the most promising, because it doesn't encounter this problem of as a constant external condition, and it can make sense. I mean, this is on the next slide. It can make sense of this meteorite scenario. You can just say, yeah, well, before and after the hit of the meteorite, there were just different external conditions, different regimes of external conditions. So I'm allowed to take, so before the hit of the meteorite, I can say that's a regime, and after the hit of the meteorite, I can say that is a regime. So it allows you to make this while at the same time being still, for the right, empirically applicable. Of course, you can just say, so empirically applicable in which sense? When the climate system is subject to a certain regime over a long enough time period, the climate coincides with the actual distribution over time. Of course, you want that for the, what you're actually doing is then you look what regime of varying external condition are we going through at the moment, and this is then your regime you're using in the climate definition. Of course, the main problem with the definition, that isn't an easy problem, is how to really exactly spell out this idea of what is a regime of varying external conditions. And climate scientists have all the different views about that. One possibility, I don't have time to go into detail, but we can discuss it later in more detail if anyone is interested, of course, is just to use ideas of Lovejoy and Scherzer, who are also concerned with how to define climate, and to say, we can define a regime in terms of the varying external, you can define a regime of varying external conditions in terms of the scale of minimum temperature variability. This is what they do. And then they arrive at, so for pre-industrial periods, for them this is something like 100 years, and for our periods it's something around 30 years. But this is just one possibility. I think the definition is the most promising, but you have the problem that you need to say what is a regime of varying external conditions. And that finally, before we move on, I mean, this is especially something when if you read Lawrence and of course the more mathematical literature on climate, what people like to do is also to consider infinite versions of definitions 1, 2, and 3. So what are you doing here? Essentially what you're doing is saying, in my model, I don't look at 30 years periods, but I blow this up so that I get in the end an infinite time period. So as time goes to infinity, this is meant by infinite versions. And while you can do that, I don't really see a reason why this is so fruitful in the following sense. It makes the mathematics easier, and that's nice, of course. But conceptually speaking, you have, of course, problems in the sense that you don't know that these distributions you're calculating over an infinite time period are really relevant for your finite time periods. And if you could solve this question, in some physical systems we actually know that this is the case, that we can go to infinity and no harm is done by that. But I think here we don't know enough to know that no harm is done by that, and so we shouldn't do it. So it's just unclear whether if you do that, you arrive at distributions which have something to do with our climate system, are empirically applicable for the cases we want to apply them. And so I think there's no reason to do that. And also, I mean, this is not relevant for definition definition 1, you can show that under the usual assumptions, the limits do exist. But for definition 2 and 3, you have these varying external conditions. And when you have varying external conditions, Kirchhoff's theorem doesn't apply any longer. So it's just not clear whether the limits exist. It really depends then completely on the details of the system, whether they exist or not. So you could even have, I mean, this is the desiderata 5, you could even run into problems mathematically if you take the infinite limits. Okay, so much really about this first class of distributions over time. Let's have a look at the second class, and I mean, which is really altogether different, and for that reason also quite interesting. So distributions over time are very different from climate definitions, but ensemble distributions. And we'll have a look at them now. So we've seen, I mean, for climate distribution over time, there were versions with constant external conditions and varying external conditions. And that's basically the same here. So definition 4 and 5 just differ in the sense that definition 4 assumes constant external conditions, and definition 5 doesn't assume that. So that's why we have two definitions here. So what are you doing with an ensemble definition? I mean, the concern is really very different here. So what you're doing here, you want to make, so the assumption, as it's usually presented by climate scientists, is to say, well, we want to make prediction at a certain point T1 in the future. And I mean, now this assumption of constant external conditions comes in. As in the next definition it will be relaxed, but I'll first discuss the constant case, because for the distributions over time, I also first discuss the constant case. So you say, well, over this time period, let's just assume the constant external conditions are just roughly fluctuating around this constant value C, and so I'm just justified to use a constant value C. It's mathematically, again, much easier if you do that. And that's also motivation why some are doing this. And then definition 4, I'll read it now, but then explain it in more detail what exactly it's really doing. Is definition 4 says, the climate at T1 is the distribution of the possible values of the climate variables at T1 under constant external condition C, given the present uncertainty in the initial values. So now this sounds complicated, but in the end it's just this. I mean, you say, well, for instance, with the temperature, you say, this is my temperature, these are my temperature measurements today, let's represent it by some uncertainty, some distribution, probability distribution. And then what you do, you evolve this probability distribution forward, an ensemble, to T1. And this is then your climate at T1. This ensemble you get when you evolve your initial conditions uncertainty forward is your climate at T1. Again, we can do that with our simple climate model. Suppose, as I write it, that the temperature is between 29.77 and 30 today. I think I've managed to get the correct today, 25th of October 2013. and let the uniform density, assume now, I mean, you can take any probability distribution, but let's just say for the moment, you say the uniform density best represents your uncertainty. Doesn't really matter, you could take a Gaussian and another, whatever you want. And then this is you have a representation of your uncertainty over this interval. Then you say, well, what I really want to predict is the climate on the 25th of October 2040. And so this is your T1. Then you take, I mean, this is really like before, the constant external conditions, you have, of course, the fluctuations around the value 1.5, because it's constantly fluctuating between 1 and 2. And so you set your constant external conditions to 1.5. And so the climate is then simply what I said, what you get if you start with your initial conditions uncertainty and you evolve it forward under your climate model, in this case under our very, very simple model 1, with these constant external conditions. And what do you get? Is what you see here. This is what you get. This would be your temperature ensemble distribution on the 25th of October 2040 with constant external conditions. And given your specific, precise initial uncertainty today. And I mean, you might already imagine from what I've said before about distributions over time that this issue of constant external conditions also causes a problem here, and it does. So like in the distribution over time case, the problem you're having is the following. You have to assume, of course, that it doesn't really matter that your climate system here is fluctuating between 1 and 2, and you just ignore that by saying I'll take this constant value because it's just neater, mathematically easier to do that. So this is what proponents have to assume, that when the external conditions are small fluctuations around a value C, the ensemble evolved to your future time point T1 under the actual evolution is approximately equal to the ensemble evolved to T1 under constant C. So the idea is it doesn't matter if you evolve it under constant external conditions or with these fluctuations. Proponents have to assume something like that, because otherwise you again have the problem that you're talking about a distribution of a model, but it's just not clear what it has to do with your actual climate system. And again, like before, I think there are doubts about that assumption. In a sense, you can illustrate it like before with a simple climate model, and then also with more complex climate models. So in reality, of course, you know it fluctuated between 1 and 2. It wasn't constant. And so what you actually should be doing, or what you're actually interested in, is the ensemble on the 25th of October 2040, which arises when your initial uncertainty, which was the uniform distribution in that case, is just evolved forward, now not under constant external conditions, but just under this actually fluctuating, periodically fluctuating external conditions. And what you get here, if you do that, so the distribution you get is actually that one. And it's the distribution which, I mean, it's clear again, looks quite different from that one. I mean, this is under constant external conditions. This is under varying external conditions. When you just do it as it is really for the real climate system we have been working with, so where it fluctuates between 1 and 2. Okay, this is the actual ensemble distribution as I write here on the 25th of October 2040 for the simple climate model given the uncertainty on the 25th of October 2040. And as I said, I mean, this is not just an anomaly that you only get that for some very simple dynamic system theory models, but you can also look at more complex models. And the fact is just we don't, of course, the best thing would be to look at the true or an approximately true, very close to true climate model and do these kinds of things, but we can't because we don't have that. And given that, we should be, I think, cautious with this condition of constant external conditions, because it can bring us into trouble potentially that we work with distributions that aren't really relevant. So again, there's a need to take the varying external conditions into account, and this is finally what the final definition does. And I should also say, I mean, this really arose out of dynamical system theory definition 4. It's sometimes still endorsed, but definition 5 is by far more popular of those two definitions, and I think for good reasons. And what does definition 5 does? Really just like definition 4, but it just abandons these conditions of constant external conditions. So it says, want to make prediction again at time point T1 in the future, given the present uncertainty in the initial values at today, and the present is denoted by T0. And then climate is simply the actual ensemble you get. You start with your ensemble with your uncertainty of your initial conditions, so your present knowledge about the weather, and in this case the temperature, and you evolve it forward to time point T1. So what you get is the distribution, as I write here, of the possible values of the climate variables at T1, given the actual path of the external conditions and the present uncertainty. And if you do that in that case, you get this one. We've seen that before. I mean, if you just really do that, you start with your initial uncertainty about the temperature, you evolve it forward to the 25th of October 2040, then this is what you get. And you see, of course, here it's heavily centered on the temperatures between 0 and 15. Okay, I think it should be clear, especially with that one. So such a definition is predictively useful. I think there's no doubt about that, in the sense that sometimes makes sense, and sometimes this is what climate scientists do, to start with an initial uncertainty that presents our uncertainty in initial conditions, evolve it forward and see what we get then, for instance, at the 25th of October 2040. So it's predictively very useful, and I think there's no doubt about that. It's still the question whether this predictively very useful notion should serve as a definition of climate. And I'll come to that and outline what it takes to be 3 problems with that definition. So, I mean, an immediate problem, I think it should be clear when you see the definition, is that climate dependent on knowledge, and more specifically, dependent on the present uncertainty about the initial values. So if you knew more or less, under this definition, about your, so the idea is, so if you knew more or less about your present temperature, then the ensemble and on the 25th of October 2040 could be different. So climate is in that sense dependent on your initial uncertainty. And this is what desiderata, the requirement 3 as it should be that climate is independent of knowledge, but it isn't. In this case, climate is dependent on knowledge, and I think that is a problem. Then a second conceptual question to the list about the definition is what you make with the past and present climate. So this definition only defines the future climate, as I've presented. There was a start with the present T0, evolve it forward, and then you get to T1. It's about the future. So the question, how should you define the present climate and the past climate? And I've sometimes discussed it with climate scientists, and one suggestion that came up is this idea, maybe the present climate is the distribution that scientists on the 25th of October 1984 would have predicted as the ensemble today, so on the 25th of October 2014, given the uncertainty in the past. But then, I mean, you immediately see that the problem, this in itself I think is slightly weird, but even if you ignore it, you have the problem here that you say, how far should I go back? Climate scientist in 1984, or should it be a climate scientist in 1983, or maybe a climate scientist in 1950? And I think that's not clear. I mean, if you apply to the future, it's clear because you know where you want your, you know that you want your predictions in 2040. But here, I think it's not clear. So here you would need to, really to make this work, you would need to fix a certain prediction lead time. But I think it's difficult to come up with a motivation for that. At least I wouldn't know how to do that. And I think you have the problem, so the definition 5 is so simply not applicable to the future, past and present, and so it's also, of course, difficult to define climate change with that definition if you can't say what the present and the past climate is. And this violates the fourth requirement. Then finally, the final point about this definition is, so usually, of course, you think that the climate should have something to do with your past time series of observations. So you have a time series of observations of the temperature, and you think that you should be able to estimate the climate from that. At least if you have good records. You know, the question whether you have good records or not is another one, but if you have good records, you should be able to estimate. But you can actually prove that for definition 5 in particular. So you might wonder, so what's the relation between the task time series and my ensemble predictions? But you can actually, for definition 5, you can prove, so if the external conditions are really varying, there is no relation. You simply can't estimate your climate from the past temperature distribution. In that case, you simply can't do that. You can do that under certain, so mathematically you can show that under certain assumptions, I mean, when the external conditions are completely constant, and when another assumption, when time period is very long, there's a relation. But I mean, for the actual climate system, for definition 5, that's not the case. You have that external conditions are varying, and given that, there simply isn't an easy relationship between your past time periods of observations and your climate in the sense of definition 5. You just can't estimate the observation. Okay, and I should also mention for completeness reason, there are of course infinite definitions, and infinite versions, sorry, of definition 4 and 5. So just as for distributions over time, what you did is you expanded your time period. Here you do the same. You essentially say, you can either essentially say you don't predict 30 years, but you predict 40, 50 and so on, and then you need the time period to go to infinity. So you can do that here too, and sometimes it's mathematically more convenient, but I would say exactly the same as for definition 1, 2, 3. It's just unclear. I mean, first of all, there's the problem, and this is even more acute here, that whether these ensembles converge, that's an altogether different matter. They sometimes don't converge. Like for the simple example I have, they don't. And even if they converge, it's just not clear whether this ensemble I get when I take the limit is just relevant for the kind of predictions I want to make, because maybe time period is so, the convergence is so late that it doesn't really help me to make my predictions in 2040. So it's just, I think these infinite versions are interesting. Of course, they're interesting from a mathematical point of view, but I think there's no reason to prefer them to the finite versions here. So Just I think two more. Yeah, I think we might. Do you have still 3 minutes?
5 minutes.
5 minutes. So then I can still, before I come to the concluding slides, give just to relate this discussion we have now to the Ipcc definition of climate, which is the following. I mean, this is from the previous Ipcc, but I've looked it up and I think it's the same. I didn't find any different in the new definition in the new Ipcc report. So what do they write? They write climate. This is in their glossary of terms, I think, as they call it. They write climate in a narrow sense is usually defined as the average weather, or more rigorously as the statistical description in terms of the mean and variability of relevant quantities over a time period ranging from months to thousands or millions of years. The classical period for averaging these varies in 30 years, as defined by the World Meteorological Organization, because they usually publish these 30 years period statistics. And then it goes on, the relevant quantities are most often surface variables such as temperature, precipitation, and wind. And then the red climate in a wider sense is the state, including a statistical description of the climate system. So as you see, it's quite complicated. First of all, you have this idea of climate in a narrow sense, and then you have, climate in a wider sense, which states is the state, including a statistical description of the climate system. But I think the most important point to take away from this characterization is vague and ambiguous, as I write here, and probably also deliberately vague and ambiguous to really make room for all these definitions of climate, to please everyone. And something like the Ipcc, of course, that makes sense because you, in a way, present them the consensus, and the consensus here is that they are quite different definitions. But I think climate in a narrow sense has these reference distributions over time, because it refers to time periods. It's why the climate in a narrow sense seems to refer to distribution over time, so to something like definition 1, 2, 3. Climate in a wider sense is, I think, left very open, because all they write is a state, including a statistical description. And of course, I mean the state, they might mean the state of the system, plus statistical description, but statistical description, of course, extremely weak, just some kind of statistical description, they don't say more about that. So, as I said, in principle, interpreted as referring to any, so climate in a wider sense could be interpreted as any of the definitions we've discussed here. So now back to the concluding slide. As I've discussed, I think, what I take to be the two main kinds of contenders, or the two main kinds of definitions which are also really endorsed, this idea of climate as distribution over time. And as I said, there are 3 versions of this more general idea, and I think they're actually quite different, so it's important to look at the different versions. And I think definition 3 is most promising in the sense that at least it doesn't immediately run into serious problems. And definition, as the other class, is this ensemble distribution, where climate is an ensemble distribution. And I think the more promising of these 2 is the definition 5, because it just works with the varying external conditions, which I think is important. But I think you do have the problem that, as I said, that you have some dependency on the knowledge that is just unclear how to define the past and present climate, and you don't really know how to relate it to the past time series of observations. Okay, good, then thank you very much. I'm looking forward to your questions.
Thank you. We have 17 minutes for questions. Yes, sir.
Could you help me understand the meteor case? I take it the meteor case is like a sort of climate atavism or something. So we're at a temperature, then it gets cold, and we get back to that same result tablet? Is that
In that case, I was simply assuming the following. All I meant for that example is you have some kind of climate before the hit of the meteorite, take 30 years before the meteorite,
sure.
Then it hits, there's suddenly lots of more aerosol and then basically because of all this dust in the atmosphere, you get that the climate variables take different values. So it's basically this idea of temperature is that before, and then it's like that. I don't consider when you go back to that, because that's then another issue, of course. But here was just meant the simple scenario. You say, well, you have an event that causes, and you could think of suddenly everyone is pumping lots of aerosol in the atmosphere, and because of this, actually, we change the climate system. And so I think this illustrates that one often, at least, thinks about the climate more in line of a certain distribution which you get for a certain configuration of the climate system. So very weighted, but just want to
okay, just to help me to get it, so how does definition 2 fail to capture that change? Because it sounds, I mean, it's just that there was one average temperature and now the average temperature is lower because of some event, who cares what it is. How does definition 2 not capture that?
Sure. So the point here is that, so I think the assumption which has to be made at the very beginning is that you would say, well, the first before the hit of the meteorite, you have a different climate from after the hit of the meteorite. And given that, so definition 2, as I presented it, all it says is that climate is the distribution which arises over a certain time period, without further specification what the time period is. And I think you probably have in mind, and you're of course right, that if I make further specification in the sense that I don't allow this and that, but this is not what definition 2 does. So this is definition which people sometimes endorse, where I just say climate is nothing more than the actual distribution over time, without any further qualifications, and what the time period should be. You know, apart from what the length, you say something about the length of the time period, but without qualifications, which time periods you're allowed to take or not. And then you run into the problem that, of course, you could take the distribution before the hit, you could take it after it, but you could also take it over it.
But isn't that a good thing? So a good thing for the following reason. It's not like when we're investigating the climate, we're only interested in one question or one thing. And it seems plausible that actually variation in what we mean by climate is actually something that we're going to want. In some contexts, presumably, I don't have something under my hat, but there might be times when I am interested in that distribution across that whole period for whatever reason. It doesn't seem to me that there's an interest and relative objective answer as to what's the climate in the case you give it.
But I think then your question is, as I said, the underlying assumption that you said one has to say that the climate before the hit of the meteor is different from the climate after the hit of the meteor. If you question that assumption and you say, then yes. But I think there's something about the idea, I would say, that you know, climate has something to do with what I formulated, what is this vague idea that climate is what you get for a certain configuration of the climate system. And if you change the system drastically in a way which the change is causally related, so to speak, to a change in your values of the climate variable, you do think that this leads to a change in the climate, and the definition can't make sense of that. But if you want a definition of climate, of course, it's to some extent also up to matter of debate. You say, I don't worry at all. I just want to dig I don't mind. I don't think that in these two cases it has to be different climates. Then definition 2 is more attractive. But I think
The suggestion was just make it interesting.
Mark.
So yeah, I have a question that really fits in with the previous one. So you have the Ipcc definition coming out quite close to the end of the talk. I was thinking about it the whole time because it seems like that actually solves the worries that you have with some of the other definitions, because it is vague, and I was wondering if this isn't really a virtue of that definition, because it captures a lot of the different ways that climate is used in the literature. So what's the motivation for trying to come up with a narrow definition if that narrow definition will fail to apply to some of the cases that you're looking at?
You know, I think it all depends on how you use it. I would agree if you say, well, if everyone knows that definition 1, 2, 3, 4, 5, and when you talk about climate, you know that with definition 1 in mind, or definition 4, or definition 5, then it's fine. But I see a problem in, I think, so what I would say to that, I think it's just very important to distinguish between the different definitions of climate. And in addition, I do think it gets problematic when it comes to definition. That's why I have the desiderata, when it comes to definition, which, in my view at least, that's what I said, where I don't know how to make sense of the idea of past and present climate, but only about the future climate, then how should I at all define climate change? And if you talk to policy advisors, of course they want to be interested in climate change, but it's not clear how to make sense of climate change. And equally, I think about, so you see, I mean, I would agree to it, I don't think there has to be one definition of climate, no. I think if there are good concepts around, they can be 10 or whatever. You know, I don't think as philosophers, which anyway, this concepts, they can be different useful concepts, but I do think that when we come back to this slide, and the definition 1 is this with this constant external condition, and this brings us into troubles. There's no need to do that, similar to definition 4. Definition 2 we have just discussed. And And definition, and the ensemble distributions, I think it's something we should think about at least. Do we really want definitions of climate which are dependent on our knowledge? You know, if you talk to policy advisors, and they, of course, if you talk to them, they would never think that if you tell them the climate in 2000, at the end of the 22nd century will be completely different from the climate today, they don't think that you're talking about something which is dependent on our knowledge. You know, they think you're talking about something which is objective and independent of our knowledge. And you don't have that definition for example. So I mean, I would agree in the sense that, I mean, I don't have per se anything against the Ipcc giving a vague definition of climate. I think that's fine, because it's true that could be different definitions that are useful, but I think we should look at all the different definitions and ask, I mean, first of all, we should always be clear which definitions we are using, also in policy context, because of course, policy advisors usually have something like definition, more like Hart's distribution over time in mind, and if you then talk about an ensemble distribution, you'll talk about different things, and that's problematic. And then second, that I do think it's also important to have this list of requirements on a definition of climate, so to speak. Because otherwise, as I said, I mean, and of course there can be some debates on that, and of course there is. So some people are much less worried about the climate being dependent on the knowledge. Some people don't mind that this is the case, but I do mind.
Okay, good. We've got 10 minutes left and 5 people in the question queue, so apologies if we don't get to everybody before the lunch break, but of course you can always talk to Charlotte Durant. Wendy, you're next.
Thanks. So it sounds like you're open to pluralism about the concept of climate, but among the ones you considered here, you think maybe only number 3 is a promising candidate. And you sort of just, it seems like the remaining question about 3 was getting a clear idea of what counts as a regime. And then you had at least a remark about maybe one way we could go was related to the sort of Lovejoy kind of work. And I'm just wondering if you have some lingering concerns about that approach, or whether you just haven't thought through yet, whether you're satisfied with that, or...
No, I just mentioned, no, it's a good question. I just mentioned it because when I gave this talk, I talked to people or somebody saying, oh, well, you know, you have this definition 3, it's completely unclear what the regime of a very So sometimes when I endorsed definition 3, people came back to me saying that's so problematic. So that's why I wanted to stress that this is a problem. I'm more pragmatic about it. I think to some extent also this idea of regimes of very external condition, you can also take something which fits your purpose and your context, so to speak. You know? And I would take Lovejoy and Scherzer's, they have the specific proposal of how to do it, and I would say that's one proposal that might work in some cases and some. I personally don't have much problem with that, but I wanted to emphasize it because others do.
So you're pretty happy with them?
I am more or less happy, but I do think it's non-trivial. I think it's all, if you go to like this proposal of Lovejoy and Scherzer, you really have to say, if you want to define it in terms of the scales of minimum temperature variability, you need to understand a lot about the physics and the physical mechanism in order to do that. So in this sense, a lot of work has to go into that, but I think that's fine. In a way, it was good, you know, just because if you do that, if you make clear if you put a lot of work in what a regime of very external conditions is, then you also take away the arbitrariness of the time period. Like for Lovejoy and Scherzer, they have a motivation why pre-industrially 100 years around and now 30 years. So yeah, thanks.
We'll go next.
Yeah, thanks. Just a brief comment. You shouldn't put too much emphasis on the Ipcc definition. So from 10 years of experience,
anyway.
I know that most scientists don't care about the glossary. So the glossary usually comes at the end and, oh my god, the glossary, and then you have to stop there. And once you start discussing about definitions, you don't reach any consensus. So there's some randomness in there. Just to give you another example, there's a definition that says pre and post-industrial refers somewhat arbitrarily as before and after 1750. Which gets us into policy trouble right now because it's somewhat arbitrary.
It's somewhat arbitrary. No, I would agree. I just wanted to give it because, especially probably more philosophers always want to know what's in the Ipcc and so on. And it's still interesting to see what they want, but I wouldn't put too much emphasis on it.
Dan, you're next.
Okay. 2 quick comments about the ensemble definitions, especially definition 5. So first, in your exchange with Wendy Parker, if I understood you right, you said that you're willing to allow pragmatic considerations for how to discriminate regimes. And at that point, someone, a defender of definition 5 might say, well, if we can allow pragmatic considerations in definition 3, why can't we do something similar in definition 5? And so our knowledge of, yeah. And then the second point, a little more generally, I think one reason why we might want the ensemble distribution definitions is because we want to talk about predictions. And so maybe something in the vicinity of definition 5 that addresses some of the concerns you have up there might be a good definition for something like a climate prediction, which of course we want to distinguish from the actual climate. One is a representation, the other is the real world.
Sure. So yeah, I mean about your first question, I think I would probably still make the distinction between, you know, of course, pragmatic considerations and the consideration that something is dependent on my knowledge. And I think they are not the same. You can't say. I would allow, in a sense, for saying, well, you know, a climate scientist who is concerned with much longer paleoclimatic developments might choose longer time periods than someone who is not, because he's looking at it at a different perspective, but still saying that it's more radical to say, to really accept that the climate here is defined as dependent on your initial uncertainty about the measurement of your climate variables. So this is what I would say to the first. And to the second, I would actually, I mean, I think it's important what I said. To the second, I would say, yes, of course, these definitions 4 and 5, especially 5, are predictably useful. But, and I wouldn't object to them being used as non-definitions, you know, and I wouldn't object to them being used to saying that's, I think what they are really doing is this is the predicted or the estimated value of the climate variable at that specific time. This is what I would say. But I think it's also important that I don't stress that, and that's why question is good. So you can, these distributions over time, you can of course estimate, you can use for prediction something like that too, climate distribution over time, and simply estimate what distributions over time you get in the future. Then you get, in a way, some kind of mixture between this and that. So you get it. Because what they do is, when definitions try to estimate something at a certain specific time point. And so you could, of course, just say, I want to estimate what my future distributions over time will be, then you have an estimate of the climate. And I think this is a predictive notion. It builds on distributions over time, and you can use it, and that's fine. So you see, I think some elements of that are useful, but I would resist calling that climate, because you can't. Climate distribution over time can be used for prediction too, and this can be used for prediction too, but just don't call it climate.
You're next.
So my question is actually very similar to the question that was just asked. So maybe I'll just press you on the last comment you had, where you said I wouldn't call these future estimates climate. But if the question is if there is a change in this thing that we cannot call climate, but it is somehow analogous to what we currently call climate, and we're trying to talk about 20 or 50 years in the future, and we're trying to anticipate, should we actually do anything differently now if we don't like what that other thing is? It's not climate 50 years in the future. Well, how do we articulate?
You can just say this is the estimated value of the climate variable, and this is what you're actually doing. You estimate the value of the climate variable. It's an estimate of the value of the climate variable given your present uncertainty.
So it just should be called estimated climate change rather than.
It is just a proposal. I mean, you know, I think the problem I have with that definition is really that you can't. I mean, of course you would say when you say think about attribution. I mean, in attribution statement, that definition of course can't be used because you don't know what the past climate and the present climate is, and that's I think that's something you shouldn't take it so lightly. But to some extent, you can. I mean, some also say call climate whatever you like. To some extent, you can also do that. But it's not a good recommendation when you think about. Of course, we have to be careful in what terms we use because it's quite important for policy advisors and so on. So if all climate scientists use definition 5, they know what's meant by that. And when they go to the past climate, use a different definition. They know what's meant by that. It's not so problematic. But it is problematic if not everyone will always know what definition one has in mind. This is what I would say.
Last question of this.
So I want to push back on the other point, the context-dependent presentist thing. So I think it seems like what you are calling definitions because there seems to be a lot more built into them than just mere definitions, right? So
Then just mere definition.
just mere definitions, right? So, but if that's, I mean, and that doesn't matter, like the term, whatever. But if it's something more than just a mere definition, then it seems like something like a conceptualization, right? It's not just that this phenomenon, however you characterize it, is what we mean when we say climate. That's sort of a definition. But if it's a conceptualization, it's sort of the way you understand the entire phenomenon, then how on earth can you have desiderata 3? Or the one with which doesn't allow knowledge and pragmatic things to enter.
I didn't say it allows pragmatic things to enter. I said, I think, it depends when you're pressing me on that. It depends when you just said it's a mere definition. If you mean by the different definition and mere stipulation that you can arbitrarily say I understand the term in that way, of course that's not what's going on. In the same way, you can also say, but to some extent, what I'm most interested in is what definitions are really useful for the science. And I do have doubts that a definition like 4 and 5, where it's not clear how to talk about the past climate and the present climate and how to estimate the climate from the observation. It's really something which is a useful notion for the discipline. That you would, when you work with something like that, and actually people are doing, there are some defenders of definition 5, and they're actually working with definition 5 if things concern the future, and working with something like definition 3 if things concern the past. If you're willing to accept something like that, I would say that probably we can do better. And choose a definition 1 where we can really talk about everything, the past, the present, and the future.
Well, let's thank our speaker.